Peruzzi at University of Milan. So yeah, let me start by saying, so I'm going to assume like everything I'm discussing today is over C. So it doesn't matter if you want to take any algebraically closed field of character 0, but since I'm going to talk about hyperkähler geometry and all this kind of geometric thing, it's more natural for me to just stick over C. Okay, so yeah, so I want to start by recalling something about hyperkähler varieties and algorithm 10. That's kind of the main player in my talk. So let me yeah, okay, so let me at least spell the word once. Oops. So let me start by talking about hyperkähler varieties and this thing called algorithm 10. I'll just write OG10 for algorithm 10. Okay, so let me start by just doing the writing down definition. So I'm going to work in the algebraic category. So then in particular for hyperkähler variety for me, it's a smooth projective variety over C. So let me call this in X. So such a variety is hyperkähler if the following two conditions are satisfied. So the first, if I look at the holomorphic two forms on this variety, okay, so I look at the holomorphic two forms on this variety, I require this is generated up to scalar by some sigma, where the sigma is actually a symplectic form. So this means actually it's a holomorphic symplectic form. It's holomorphic two form that's non-degenerate at every single point. And moreover, I need this sigma to generate this all the holomorphic two forms. Okay, so this is the first condition. And the second condition, I want to put down some restriction on fundamental group. I assume this variety is simply connected. So of course, when I say this, I mean you take the analytic topology of this smooth projective complex variety, view it as a complex manifold. Okay, so actually a little remark here, the condition that I'm writing down here is actually a so-called irreducible holomorphic symplectic. So irreducible holomorphic symplectic. You have a holomorphic symplectic form, and irreducible basically means you have only up to scalar this form, and this fundamental group is 0. But actually, this is equivalent to the.
Can you just quickly remind us, symplectic, you mean alternating? What exactly is symplectic form again?
So this is an alternative form. And now every point I need this alternative two form to be non-degenerate.
Non-degenerate, okay.
Yeah, non-degenerate at every point. Yep. So, but this is equivalent to the more differential geometric definition of hyperkähler, which I won't really recall in this talk. Okay. So this is basically the definition of hyperkähler. Okay. So let me actually start by writing down some examples of this. So the very first thing, so I can think of this in dimension 2. So I need this two form to be non-degenerate. So in particular, the complex dimension of this kind of variety is always even. So in dimension 2, if you think about this thing, this is just the canonical bundle of the surface, and then ask this thing to be generated by a symplectic form, which is just basically trivializing this canonical bundle. And moreover, the restriction on the fundamental groups tells me there's only one kind of example, which is basically K3 surfaces. So K3 surfaces are the only example. Only examples. Okay. You have abelian surfaces, which is also K-trivial, but the fundamental group is not trivial. Okay. So this is actually the starting point. And so now I want to ask the question, like, what's really in higher dimension? What's happening in higher dimension? Okay, so all the known construction in higher dimension of smooth projective examples are actually somehow done by algebraic geometry. So in higher dimension, is dimension at least 4. So what we can do is we can take moduli space. Take moduli space of stable sheaves stable sheaves on K3 surfaces. Okay. So on K3 surface, I can introduce this notion of slope, which is basically saying I fix a polarization that can intersect the first term class of a sheaf by this polarization, giving me the degree. And I can look at the rank, the quotient is the slope, and I just basically consider slope stable sheaves. In this kind of moduli space, I'm actually kind of secretly assuming the character I'm fixed, the topological invariant I'm fixing is actually primitive. So I have only stable sheaves. The moduli space is smooth and projective. And it turns out that gives me actually examples of higher dimensional hyperkähler varieties. Okay, so actually, let me just mention this. So there's a similar construction, which is equivalently interesting, using abelian surfaces. We can take stable sheaves, a moduli of stable sheaves on abelian surfaces. The problem here is like you will have some non-trivial fundamental group, and different from dimension 2, which you can do nothing. In higher dimension, you can just write down the Abelian morphism and take a fiber of the Abelian morphism. That will actually kill the fundamental group and give you some example of hyperkähler variety. Okay, so you can just do some similar construction using this abelian surfaces. Okay, but this is not really the thing I'm going to focus on. So besides these two types of examples, there are actually two more special families. So this is a special family, which is actually constructed first by O'Grady, a special family, which is usually known as O'Grady hand. Okay, so let me actually explain the construction. So once again, I'm going to fix the K3 surface. So S is my K3 surface. And I'm actually going to fix a vector in the numerical Grothendieck group. When I say K num of S, this means the numerical Grothendieck group of the surface. In concrete word, what I'm saying is like I'm fixing a rank, a first term class, and the second term class as topological classes. Okay, so this is really what I'm doing. I'm considering sheaves of a fixed rank, a fixed first term class, and fixed second term class. Okay, so moreover, I need this v squared equal to 2. There's a Mukai pairing on this lattice, and I need the v squared under this Mukai pairing equals to 2. In practice, this is just to guarantee like the moduli I'm eventually going to get is 10-dimensional. Okay, this is just some dimension condition. That's the way we can think about it. Okay, so now I consider the moduli space. The moduli space, I will write this as M2V. Okay, so notice I'm multiplying this by 2. So of semi-stable sheaves of class 2V. Okay, remember this V is just the data of rank, degree, and second term class. Now I want to look at the sheaf of topological invariant 2V. Okay, so what's actually happening about this? Okay, what's happening about this moduli space? Okay, I'm having some little problem with the whiteboard here. Oops. It's a good exercise. Is it reasonably clean? Okay. Sorry guys, I mean, I haven't used this whiteboard for a long time, as you can imagine.
Yeah, that's clean. Yeah.
There's supposed to be like a little oil on the top,
Yeah.
but now it dries out. Okay, so yeah, let's leave with this. All right, so okay, so let me take the moduli space of semi-stable sheaves of rank 2B. So now something happens. Let me draw a picture like this. So something happens which is a little bit different from previous. So now I have this moduli space is actually 10-dimensional. The dimension is actually 10. So this is my M2B. So inside here, there's a big open set, which is actually characterizing the stable sheaves. Okay, so I'm looking at semi-stable thing, but actually, if I look at the stable sheaves, this is actually an open set in this moduli space. And this is coincides with the smooth locus of the moduli space, which is also the smooth locus. Okay, and moreover, there's actually a strictly semi-stable locus. So this is the strictly semi-stable sheaf. Semi-stable sheaf. Okay, so up to something called S equivalence, the moduli is characterizing this kind of sheaves only up to some S equivalence. So what you can imagine here is, can you imagine this kind of sheaf are always of the form A1 plus A2, where this A1 and A2, this A1 and A2 are actually stable, but of half of the character I have there. So they're actually stable sheaves of character V. Okay? So this is the effect of having a non-primitive character, twice of the character V here. That's going to give me some strictly semi-stable sheaves in this moduli space. And actually, this will be a singular locus of my moduli. Okay, so this is actually the singular locus. The singular locus of my moduli space. Okay, so this is actually what's happening in this moduli, and this guy is 8-dimensional. But since it's just given by the direct sum of this moduli, so you can imagine this is actually isomorphic to sim2 of this MV. Okay, so this is actually the little background on what's happening with this very special moduli space. Okay, so why do I care this? So this is actually going to give us the O'Reilly 10. So remember, at the end, we want to have some hyperkähler variety, which by my definition has to be smooth. So now I have to resolve the singularity here. All right.
So
yeah. Okay.
May I ask this?
Sorry, is there a question?
Yeah, I see. So in the construction here, you have the Mukai vector v squared equals 2. So why?
Yeah, that guarantees this guy is 10-dimensional and this guy is 8-dimensional.
Oh, okay.
Yeah, so it's more like a dimension condition. You can imagine this.
So basically means if you change the 2 to other numbers, you get different dimension.
Sorry, say again.
If you change the v squared equals 2 to another number, say v squared equals 3, 4, is that
so
possible?
v squared has to be always an even number.
Okay.
And the dimension of the moduli is v squared plus 2. But I mean, you can always do that, and your moduli always have this kind of stratification with just some different dimension. But the thing I'm going to say next will not hold.
Okay.
So only in this situation you can resolve and get a hyperkähler manifold. So that's why I pick this v squared equals 2.
I see.
Yeah.
Okay.
All right. Okay, so let me write down the theorem. This is due to already. The first one is actually due to already, which is saying that there exists a hyperkähler resolution which I'll write it as M2 resolving this M. So for this M, I mean this M2B. Okay, so this is the first thing. So by hyperkähler resolution, I mean you have a resolution of singularity, which is itself is a hyperkähler manifold, a hyperkähler orion. Okay, so the second thing, so the original construction of this Aurelia of this resolution is very complicated. So we have to go through this, the so-called curve resolution of this GIT and so on and so forth. And later, this Len and Sauger provided actually a simple description of this resolution. So the resolution is just the blow up of this M along the singular locus. Okay, so I view this as a sub-variety. It's a subscheme, but with reduced structure. So in particular, this is actually a sublocus inside a sub-variety inside M. Okay, and I simply just blow up this reduced subscheme, and that's actually just going to give me this M2. Okay, so this is actually the thing I'm going to use at the end. And so I think if we go to just also mention, so similar to before, you can construct the already six. It's a 6-dimensional hyperkähler manifold from the abelian surface. Okay, so the construction is very similar. You just pick some non-primitive character and ask for a resolution of singularity. Okay, and also back to what Fei just asked me. So it's known that only when your v squared equals 2 and you take twice of such a vector, then you can have some hyperkähler resolution. So if you take higher multiple, you take some different v squared, then actually you have resolution, of course, but they won't be hyperkähler anymore. Okay, so in some sense, this is the only example that you can produce out of this non-primitive character thing. Okay, the proof of this thing relies on some, like you have to study very carefully the local singularity of this moduli using, this is a moduli space, so you can use deformation theory to control the singularity. Okay, so yeah, let me now go through the proof. So the second part, so now once we have this already, I want to, okay, so sorry, there's one important sentence I have to say. So moreover, I give you all these examples, moreover, so all these examples I mentioned before have deformation which are still hyperkähler. Okay, so what I mean by this? So first you can see that you can deform the underlying K3 surface. And when you deform the underlying K3 surface, as long as your character remains algebraic, you can take the moduli and the moduli will give you some deformation of your hyperkähler variety. Okay, but in higher dimension, there's always either one more dimension or two more dimensions of deformation of the examples of the moduli space I had before. That's not coming from the deformation of underlying K3. Okay. So there are some generic hyperkähler manifold in this family that's just not arising as moduli of stable sheaves on K3 surface. Okay, so in some sense, the moduli space here are really some special sublocus in the moduli space of the all hyperkähler. So they're generic ones that's not coming this way. Okay, so actually this is a current theme somehow of this study that you can deform this K3 surface to some triangulated category so that actually this generic hyperkähler also have a moduli interpretation. But I mean, I'll just, so the thing I'm going to talk about is like one instance of this kind of big philosophy. Okay, so the second part, let me actually state my result, which kind of thing I want to actually prove. So result, state two equal theorems for cubic fourfolds. Okay. Okay, so let's say I take an X, which is a smooth cubic fourfold. So I always assume my cubic fourfold is actually smooth. smooth cubic fourfold. That's actually, like this is a hypersurface in P5 given by a cubic equation. So let me actually write down the theorems. Okay, now it's better. So the first result is something that people studied a lot in recent years. So once I have a cubic fourfold, I can look at this family of hyperplane sections of this. Okay, so this P5 dual will actually parameterize the hyperplanes in P5, and I just use this hyperplanes to cut my X. This curly Y is the universal hyperplane sections. Universal hyperplane sections of my X. So then in particular, each fiber here is a cubic threefold. It's a hyperplane section of the cubic fourfold, the cubic threefold. And inside here, let me just call this P5 dual smooth, which is actually corresponding to all the smooth hyperplane sections. So this is the open side, it's the complement of the dual hypersurface. Okay, so like once you have, if you have a smooth cubic threefold, so for each smooth cubic threefold, which I'll call it Y, so there's a typical thing, geometric object that you can consider, which is the so-called intermediate Jacobian. It arises from the Clemens-Griffiths study of the irrationality of cubic threefold. And so let me write down the definition here is just to take all the H21 on this Y, to consider the integration of this kind of three forms over the topological cycles inside the space. And of course, the pure rate is unique, is determined up to element in the H lower 3. Okay, so this thing will embed it into this complex space as the lattice, and we'll take quotient. You have actually a complex torus at least. But in this situation, since I only have H21, then this is naturally polarized, and this actually gives you the abelian variety structure. So this is actually a 5-dimensional abelian variety. Okay, so this thing is a 5-dimensional abelian fivefold. Okay, so this is known as the intermediate Jacobian. Okay, of this cubic threefold. This is actually somehow a typical thing people consider associated to a cubic threefold. So the thing I'm doing now here is like I don't want to consider one of them, but I actually want to consider with respect to this family. So this is actually known like in this situation, this thing comes naturally in a family, homomorphic family. So this gives a family. So I'll write it as J twist, which is actually over the smooth locus of this P5 dual. Okay, so whenever I have a smooth cubic threefold as the fiber of this fibration, I can replace it by this abelian fivefold. And in this way, this gives me actually a family of abelian fivefold over this this open set, parameterizing smooth cubic threefold. Okay, so a little word. So why there's a twist? So it turns out there are actually two different families you can produce out of this fibration. So the thing I'm considering here is the so-called twisted family, and there's also untwisted family. I don't want to go through the details of this. So the way I always imagine this is, if you have a family of curve, you can look at the family of Picard 0, or you can look at the family of Picard 1. So of course, Picard 0 and Picard 1 of a curve are isomorphic to each other. But we'll do this in a family, the fibration structure could be different. Okay, so here I'm actually looking at some kind of twisted family. So this would be corresponding to, like, say, degree 1 cycles of this cubic threefold. Okay, yeah, I don't want to go through too much about the definition of this thing. But the interesting thing is actually a theorem. Okay, so this was actually first proved by Claire Bozan. So I'll say more about the history of this thing. And then recently proved by Julia Sakar. And also this comes out of as an outcome of our paper. So roughly speaking, the situation is the following. So there exists actually an already 10. Okay, let's say an already 10. I really mean something that's deformation equivalent to the already 10 I constructed. So you can take a K3 to do the singular moduli space and do the resolution, but also I allow a deformation. So something deformation equivalent to this already 10 example, I'll always call them already 10. Okay, so there exists actually an already 10 hyperkiller variety. Let me give this thing the name N. And on this end, I have actually a Lagrangian fibration structure. Okay. So let me write it down here. I have a Lagrangian fibration structure. So this N will be mapped to some base B. So we know this B has to be 5-dimensional. And by Lagrangian fibration, I mean, if you look at the fiber here, and you look at the smooth locus of the fiber, so that smooth locus will be actually a Lagrangian with respect to the symplectic form that I have on this end. Okay, so typically the fibers will be some abelian 5-fold, and actually that's actually going to compactify with what we have here. So this is compactifying this intermediate Jacobian fibration over P5 dual smooth, and then on which you have this twisted family of intermediate Jacobians. Okay, so this is actually the.
Okay, can you explain again what the Lagrangian condition is? I didn't get that exactly.
So a subvariety here is Lagrangian if it's actually Lagrangian with respect to the symplectic form. Okay.
What does that mean to be Lagrangian with the symplectic form?
So that basically means, if your symplectic form locally is x1 batch x2 plus x3 batch x4, then this thing will involve x1 and x3, for example. So that's basically, so the restriction of this form will become 0.
Oh, okay. Mm-hmm.
Yeah.
Mm-hmm.
And this Lagrangian fibration means every fiber is Lagrangian. Okay. Yeah, so let me say what happens here. So the little history on this question. So it was a result of Laza, Sakar, and Wadang. They show actually the existence of this kind of compactification for a non-twisted, for untwisted family region, and for very generic, very general X. So that means in the model of cubic fourfold, we have to throw away countably many divisors. And for the remaining cubic fourfold, and for the untwisted family, which I didn't really introduce, they can show the existence of this. And then Wadang actually generated this into a twisted family, and actually also very general X. Okay, and later somehow Sakar, sorry, later Sakar actually showed this thing for she did this for both untwisted or twisted, and actually any smooth X. So her work is based on the previous two works. So she basically argued that once you have this kind of thing, then using some deep result from directional geometry and some beautiful argument, you can extend this to any smooth cubic fourfold. And somehow our thing is along a different line in the sense like it's actually independent, in particular it's independent of all the previous work. So we somehow find actually somehow a moduli, more like a moduli construction of this compactification thing. So it's more closer to the original construction of all this kind of algorithm 10 as the resolution of some singular moduli space. We can reprove this result, and this is independent of the previous work. Okay, so this is actually the first geometric consequence, geometric result that I want to mention. All right, so the second is some closely related question in some sense. Oh, okay, so the second, so let this, I take the Hilbert scheme of subschemes of this cubic fourfold of Hilbert polynomial, either 5t or 4t plus 1. So this be the, let's say, the main component. So this kind of Hilbert scheme may have many components. I'm looking at the main component, which contains, the smooth curves like this. Main component of the Hilbert scheme of, in this situation, if you compute, the curve is of degree 5, and you can see the curve has to be of, has to be elliptic curve. The elliptic quintics, we call it. And in this situation, it's a rational curve of degree 4. So it's called rational quintics. Okay, so look at the Hilbert scheme of this kind of curves inside Y. Okay, so the theorem, this was conjectured before, and the theorem is if you look at the so-called MRC quotient, the maximally rationally connected quotient of this Hilbert scheme of elliptic quintics, Hilbert scheme of elliptic quintics, and the Hilbert scheme of this rational quintics. This is actually given by some algorithm 10. Actually, OG 10. Okay, so remember this MRC quotient are only well defined up to birational equivalence. So basically, precisely what we are saying is like you can realize this as some variety that's birational to OG 10. You can choose OG 10 representing the MRC quotients. Okay.
Yeah, can you say a few words about these MRC quotients?
So essentially, this is actually so every time you have a variety, you can construct a rational map from this variety to the MRC quotient of this variety. In the sense that the fiber here, so that if you look at the generic fiber here, it's rationally connected. And so the target here doesn't contain that many rational curves anymore. So in some sense, you're contracting maximally, so the rationally connected part inside this variety. Okay, this is a slightly subtle thing to actually construct. But actually, so there's using some birational geometry can show like there will be such a thing. In this kind of situation, so typically what's happening is you look at the Hilbert scheme. So there will be some fibration, like a PN fibration, like a productive fibration. And then we'll contract down. The base here will have a symplectic form. So in particular, it won't have many rational curves. It won't have rational curves covering the whole base. So that's typically the way we imagine this MRC quotient in this situation.
Okay. Does MRC stand for minimal rational curves?
No, this is maximally rationally connected.
Okay, maximal rationally connected.
Yeah, maximal rational connected quotient. Okay. I think the classical examples of rational curves, this is the only remaining case of rational curves on cubic fourfold. For lines and conics, it's known that the MRC quotient is a hyperkähler fourfold. So it's the classical thing of finite variety of lines. For twisted cubics, it was studied in this work by LLSVS. It's a hyperkähler eightfold. And actually also the Yung and Star actually prove when the degree is greater than or equal to 5, you can always have a symplectic form on the Hilbert scheme itself. So the Hilbert scheme is the MRC quotient. No, sorry. Depending on the degree is even and odd. Sometimes you can quotient out one dimension, sometimes you can't. Okay. But this dimension 4 case is actually the only remaining thing. And somehow this comes up in the special hyperkähler algorithm. All right. So this is the two little geometric results that I want to mention here. So I think I have something like 10, 15 minutes. I will just briefly give you an idea of how to really prove this. So what's actually, where's this hyperkähler thing actually coming from? All right. So actually the proof here goes.
Sorry, before you go, the last thing, there's you have in the definition a y. What is this y supposed to be? So these quintics are in.
I'm sorry, this is x.
Oh, okay.
This is the cubic fourfold x.
And x was a smooth. What x again?
Yeah, it's the cubic fourfold in smooth cubic fourfold.
Oh, okay.
Fourfold x.
Oh, okay.
Yeah. All right. So I'll just briefly explain where does all this hyperkähler thing come from. So how do I produce this algorithm from this x? Okay, I'll fix the letter. So x always means a smooth cubic fourfold. Okay, so how do I produce this algorithm from x? So this goes into some construction that we do on the level of derived category. So I take dB of x to be the bounded derived category of coherent sheaves on x. So every object inside here is just somehow the complex of coherent sheaves, a bounding complex of coherent sheaves on x. And moreover, this is a derived category in the sense we identify a quasi-isomorphism through some localization procedure. Okay, but the upshot is like this thing has a so-called semi-orthogonal decomposition. So I'll explain in a second what I mean by this. Okay, so it has sorry, everything is x. So this is something called quintiles of component, and you can just put in 3 line models. Okay, so this is actually a semi-orthogonal decomposition. So let me write down. So I have a semi-orthogonal decomposition. Okay, so in particular, that means the following things. So that means, so this quintiles of component, this guy here is called a quintiles of component. This thing is in some sense defined to be all the elements inside the dBx, such that there's no home in this direction. There's no extension in this direction. So if I compute the extension I from O1 and O2 to this E, I should get 0 for any I. Okay, I do not allow any extension in the opposite direction in this semi-orthogonal decomposition. So it's easy to verify this kind of condition defines a triangulated subcategory of this. And also these things, they are actually so-called exceptional object, but the actual is I view them as the triangulated subcategory generated by this object. So for the special property of this object, actually that's you could each subcategory here is equivalent to dB of a point. It's basically just vector spaces. Okay, so this is the definition of this cumulative component. And it's a decomposition in the sense like everything together will generate this dB of x under extension and shift. And it's a semi-orthogonal decomposition in the sense of this kind of condition. You don't have homomorphism in the direction from right to the left. Okay, very roughly, that's what it means. But the important thing for me here is I can really define this kind of cumulative component. And this thing actually has two important conditions. So the first thing, so this is a so-called case 3 category. Somehow you can imagine this as a generalization of dB of a case 3 surface. So in particular, this means you can look at the Serre functor. This thing has a Serre functor, which is given by a homological shift by 2. So what this precisely means is in this category, so if you write down the cohomology has actually a Serre duality just as that of a K3 surface. Okay, so let me write it down. So you compute the Hall from E to F in this cumulative component. This is always going to be the x2, right? From F to E in this cumulative component. Okay, for any F and E. Okay, and moreover, this is functorial in both vectors and so on and so forth. So this is what I mean by the Serre functor is shifted by 2. So you see, like this is precisely what you have on K3 surfaces. Okay, so this is kind of the important question going into this. And more, if you this is actually a kind of a interesting phenomenon. So this guy is isomorphic to dB of some K3. It is equivalent to some dB of some K3 surface for special x. Okay, for generic x, actually this is not true. You just get some triangulated category, but it doesn't come from dB of some geometric surface. But for some special x, this kind of thing is actually true. So you really get this thing is sometimes geometric. Okay, so this is some kind of a useful fact about this category. But this is like generalizing what we have as a K3 surface. Okay, so what we need out of this thing is the following. So this, I can only say this in a very brief term. So this is a result due to Bayer, Lahoz, Macri, and Stellari. That so I'll write it in short term. So there exists a so-called Bridgeland stability condition. There exists a stability condition on this cumulative component of x. Okay, so even though this is a triangulated category, but we can construct some kind of stability condition, just in very similar to the slope stability on a K3 surface. Okay, so this stability condition, I won't really give you the definition. That takes probably like 20 minutes. But so this consists of two data. So in particular, one part of this called the heart of the T structure tells you which kind of thing you should consider as a sheaf in this triangulated category. You know, if you have this kind of direct category, object inside here are complexes typically, but you can identify sheaves as complex supported at degree 0. And so this part of this thing will tell you which kind of thing you should view as a sheaf on this K3 category. It's an abelian category sitting inside this triangulated category. And the other part of this data will give you a slope for every object inside this category. So we'll put these two things together. We have a notion of a slope and we have a notion of what's a sheaf. Then we can talk about really moduli of a stable object, just the analogy to a moduli of stable sheaves on K3 surfaces. Okay. So even though I'm actually giving you these definitions in a very sketchy, somehow hand-waving way. This only thing I'm trying to convince you is this will replace the role of K3 surface. Well, this will tell you which kind of thing are analogous to stable sheaves. Then we can study moduli space. Okay, so this is actually the theorem, the first part of the theorem. The theorem, let me take a V. We can talk about the numerical Grothendieck group of this Kuznetsov component, just as what we did for a K3 surface. And once again, we have a Mukai pairing, and I put down this kind of condition on the dimension. Okay, then if I look at the moduli space, which is the moduli space of stable objects. So now I can only talk about stable objects in this category of this vector 2V. This is actually a projective variety, or better, I mean, it's actually, you know, the good moduli space here is the projective variety with the hyperkähler resolution. Hyperkähler resolution of really 10 type. We can find out really 10. That is the resolution of singularity of the singular projective variety. Okay, and moreover, just similar as before, you can blow up the singularity of this this projective variety, and that's actually just the hyperkähler resolution here. Okay, so this is purely in analogy to the previous result of O'Grady and of Lange-Sauger, that how you have a hyperkähler resolution, and how this thing is actually precisely resolved.
So in this example, you said there's special axis for which you actually have a K3 surface.
That's
so
right.
If you, in that case, that is the K3 surface that you're going to do the O'Grady construction.
That's right. Yeah. Yes. So if you specialize to special X, then actually you're just doing the old construction for the K3. That's a very good point. And actually, the goes through the whole argument a little bit. So, I mean, in some sense, the non-emptiness of this kind of moduli space coming from deformation argument together with the non-emptiness of moduli space of this K3 surface, which was known before. Yeah, that's a very good point. Okay, so yeah, I think I'll try to, so there's something, this is the first theorem. Okay, so but you see, like, I mean, I just have some very abstract thing. I didn't really have anything that's connected to geometry. So how do I really obtain the hyperkähler computation of the intermediate Jacobian together with all this statement about the MRC quotient of Hilbert-Stein? So this is always the second part of this kind of project, that we have to do some concrete geometry in the sense that once I fix a particular V, I want to understand what this moduli space is parametric. So this is actually the second important thing. So I think I won't really introduce all the notations. So maybe I'll just write this in a very sketchy way. So for a particular price of this V, we can understand the stable objects inside this M2V. Okay, so let me do not call this a theorem. So we can understand that the stable object inside M2V is related to geometry. Okay, so precisely, let me at least write down something here. So I can take the V to be the class of the PL, where this L is a line inside my cubic fourfold, and this PL is an object inside the Kuznetsov component of X, which is given by the following extension. So if you do the computation, you can see that O-1 on this shifted by 1 on this cubic fourfold has a unique extension to the ideal shape of the line. So that's actually going to give you a unique extension here, and I'm taking V to be the class of this guy. Okay, this is my V. But actually, we can also prove this is actually a stable object of character V. But now I want to understand 2V. This 2V is actually some old friend for people studying like vector bundle, cubic threefold, and so on and so forth. So what's the stable object inside F2V? So I can take a gamma, which is an elliptic quintic. Inside X. Okay. So you can just compute the dimension and convince yourself for generic elliptic quintic, it's actually going to span the P4. So it's containing X, but it's actually containing a hyperplane section of X. But this is actually contained in a hyperplane section of X, which I'll call it Y. So this Y is a cubic threefold. So I can consider the following extension. Take this, and I'll just do an extension of E gamma. And this is going to go to an ideal shape of gamma in Y twisted by 1. Okay, I can look at the following extension. So this guy is a rank 2 vector bundle on this cubic threefold, but I'll view it as a torsion sheaf of X. And it turns out this thing is actually inside my Kutuzov component. And moreover, this thing for generic gamma, this is actually stable of character of class 2V. Okay, so there's an open set of the moduli space that's actually parameterizing this kind of torsion sheaf on my X. Okay, so yeah, unfortunately, I won't really be able to go through the rest of the geometric argument. So for example, this is actually the connection between this moduli space and the Hilbert scheme of the MRC quotient of Hilbert scheme of Hilbert polynomial 5P. So what you see here is like for each gamma, that assigns an E gamma, which is a point inside this moduli space. So that induces a dominant map actually from the Hilbert scheme of gamma to actually this moduli space. And the existence of a symplectic form of this guarantees this is, once you have this has to be the MRC quotient. Okay, and somehow there are more refined result about like what's the moduli of this thing. If I view this as a vector bundle of Y, so that's the thing related to the to the intermediate Jacobian of Y, and so that's how this moduli space is related to the intermediate Jacobian fibration. Okay, I won't really go to that part, but at least let me say like first we have some moduli from this kind of categorical stability construction, and then we understand the object in the moduli, and then we can relate to the geometry. This is usually how my argument goes. Okay, yeah. Sorry, I think yeah, maybe I should stop here. Thanks a lot.
Thank you. Thank you.
Thank you. Yeah. So basically, so here you're seeing the modular space you constructed. You have you can realize this one as a concatenation of the intermediate Jacobi family, right?
That's right. Yes.
So is that clear? You know how you can
so basically just you know I can look at the moduli of this kind of thing on cubic threefold.
Okay.
And it's known that moduli space is birational to the intermediate Jacobi.
I see.
And then I can start vary this Y. So on one side here, I really just get the intermediate Jacobi, and on the other side, I get this moduli. So at least I know the intermediate Jacobi is birational to this guy.
Okay.
And moreover, there's some kind of fibration structure on both sides that's compatible with over an open set. So from there, this is actually some ingredient of Matsushita on this Lagrangian fibration hyperkähler variety. So once you have this, and if you can control the indeterminate loci to be small enough, then basically the birational geometry guarantees that you can find a birational model somehow admits this Lagrangian fibration. So eventually that commodification is not really the resolution of this thing, but it's birational to the resolution of this act. Yeah, there are some more classical geometry, very beautiful classical geometry, telling me actually, so this M-tilde doesn't really compactify the intermediate Jacobi. So there's a very concrete there's a very concrete flop that I have to perform. And after that, I should be able to get this Lagrangian fibration. There are a lot more here.
Yeah, it's very interesting.
Yeah.
Okay, good. So
Thank you so much. And you know, I really love also your presentation on an actual whiteboard.
Yeah.
Are you in your office now, or where are you doing this?
I mean, this is my office. I haven't come in for like, I don't know, 2 months, 3 months.